Where I come from, we have universities, seats of great learning, where men go to become great thinkers. And when they come out, they think deep thoughts, and with no more brains than you have. But they have one thing you haven't got, a diploma. Therefore, by virtue of the authority vested in me by the Universitatis Comitiatum e Pluribus Unum, I hereby confer upon you the honorary degree of Ph.D. Ph.D.? That's Doctor of Thinkology. Sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, joy! I got a brain!
Way off, way off, way off. Anyways, yeah, no. So I'm not going to tell you what the Scarecrow was wrong about, but no good. Not the Pythagorean theorem. I don't think you have a brain anymore. Anyways, this is the Pythagorean theorem. In a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. Get it right, Scarecrow. You've been trying for almost 100 years at this point. But no, maybe more like 90. I don't know when that movie came out exactly. But anyway, Wizard of Oz. There's where I want to start things here. Okay, so you're watching this video because we tried to do that proof as a class. I thought we were pretty darn successful. I got my list of names here. We called on. You helped us out. We kind of got this proven. You want to prove this freaking Pythagorean theorem. In a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. Okay, so here's your given diagram here. This is pulled straight up on Google Classroom. You're here because honestly, like when a teacher's writing something in front of you, it can be hard to write down. It can be hard to see. It can be hard to pay attention the entire time. So maybe you're going back to rewatch this to be like, okay, I need to put this on my homework. So this time I'm going to watch the video and I can really isolate maybe what I didn't put down. Okay, so you're probably not even watching this whole video. You're not listening to me right now. Anyways, all right, so here is our generic diagram here. Okay, we can have any diagram we want to prove this one. So I suggested this one. This is even the one in your freaking textbook. So, right, the idea is if we have a right triangle, let's just say C's over here, right? We have a right angle. I'll go further here because it's not necessarily isosceles. That's not a right angle. Maybe more like this. And if we have a triangle ABC, then the legs, which we will denote as B over here, and A over here, right? Those are the lengths of the legs, okay? The lengths of the legs. The sum of their squares, right? A is a pretty big freaking square. Look at that. Wow, something like this. That's too big. That's too big. Maybe something like this. B is a little smaller, but I don't even have space for it, okay? That square plus that square is going to equal this freaking huge square of C. A squared plus B squared equals this freaking huge C squared because C, that hypotenuse, pretty darn large, right? That big here. Okay, so one other thing to notice, we noticed in class here, A is a lowercase value because that's one of the legs. It's opposite of angle A. B is opposite of, B, the length of this leg is opposite of angle B. And C, the largest side of this triangle, the hypotenuse, is opposite of angle C, okay? So that's how we have this set up. And we can just draw this diagram anyhow, and we can prove this. A squared plus B squared has got to equal C squared. Or in words, right, because you don't always have those variables for your right triangle, freaking Pythagorean theorem problems. In words, right, you're going to apply this to any right triangle where just the square of the hypotenuse has to be equal to the sum of the squares of the legs. And now let's see why that's the case here. Well, give me a triangle, okay? And what you give me is this. We're just doing a generic right triangle ABC with angle C is a right angle. That's what you have, okay? That's our given premise of this, right? You can draw the diagram here as generally and loosely as possible, not specifically. And we can prove this about any right triangle. So might as well do it with right triangle ABC, where we got our arbitrarily, we're choosing that angle C is the right angle. All right, so the way we prove this is through 6-1, right? That's the first thing. Let's just hammer through this. I know you helped me out through this. I'm still going to do this as well. It's my 4th time proving this one today. Hey, yeah, me teacher, it's repetitive. But check it out here. The way we did this was, well, we introduced this guy right here. What's this? That's the altitude to the hypotenuse of this right triangle. Any right triangle is going to have an altitude. Right, any angle of a triangle is going to have an altitude. So we're going to care about the angle of the altitude to the hypotenuse because we have theorems from section 6-1 that can help us get to the Pythagorean theorem. So what we're going to do here is we're going to draw, okay, the perpendicular 2, and I'm writing more words in this than I did in class because, like, it's a video. I'm not time constrained like it was. They're 35-minute periods, very short here. We're going to draw the perpendicular to BA through point C. Okay, through point C. So that would fit the definition of an altitude. Through point C, that's a vertex of the triangle, perpendicular to its opposite side. Okay, that's what an altitude is. Altitude is vertex of a triangle to the opposite side in a perpendicular manner, or to the line containing the side that's opposite. In a right triangle, you're always going to hit that hypotenuse. Okay, so here, through a point, that's the justification. Why am I just allowed to draw that altitude? Well, that's just the perpendicular through to BA through point C. That's an altitude there. The reason why I'm able to draw a perpendicular through point C to line BA is that through a point outside a line, there is exactly, all right, writing this in, right? We're writing down the whole proof there. There's exactly one perpendicular that can be drawn. My handwriting's hard to read, so maybe hope you're listening to me so you get it there. Through a point outside a line, there's exactly one perpendicular that can be drawn, okay? There is an existence of a perpendicular that would go to this line opposite, and it's unique, okay? Existence and uniqueness is something that I talked about last semester, but right there it is. Right there it is. We're allowed to draw it in. Boom. Introduce an auxiliary set to help prove this thing, an auxiliary line, as your book calls it here. Okie dokie. So we got an altitude in there. That's going to help us because we know that altitudes do some crazy things with the legs versus the hypotenuse, or the altitude itself versus the segments of the hypotenuse. So we already have C put in here. C, again, is indicating that is the length of the hypotenuse. A squared plus B squared is C squared. That is what we need to work towards. What's going to help us get us there is talking about the segments of the hypotenuse. So let me actually indicate what we're going to give variables for those in this one, because B is the geometric mean between C, which is the whole hypotenuse, and the segment of the hypotenuse that's adjacent to this leg of the large triangle. Very hard. Like, your mind's melting as you're hearing that. It's complex getting it to connect together, but just follow my lead here. B is the geometric mean of D and C, okay? Because it's the geometric mean between this segment of the hypotenuse next to the B here. Look, D is definitely smaller than B, but C is larger than B. B is the geometric mean. It's kind of in the middle here, okay? So that's the reason why we introduced the altitude, is now we have B in an equation, and it appears twice. That's going to help us to B squared into this proof. Look at this. We want to prove this, thinking backwards, always looking forward to like what we want to get to say. We want to get to proving C squared equals A squared plus B squared. The square of the hypotenuse equals the sum of the square of the legs of each leg. Here, okay? So the reason was, so what I just said right here, we're going to say it too about the other leg, okay? What about this? A is the geomean of what? Well, actually, I haven't actually assigned a variable for this segment of the hypotenuse that's actually adjacent to side length A. So why don't we call it E? Why don't we call it A? Here we go. A, B, C, D, E. There we go. So one segment of the hypotenuse is length D. That's adjacent to B. The other one is E. They add up together. What do they become? They become C. Okay? So you feel me? Let's follow this one here, man. It's all about seeing what follows, right? In the world here. A is the geometric mean of E, okay, which is what we just put there, segment of the hypotenuse. You with me? You follow me? I don't know. E and C. There you go. Okay, so the reason why we know it's the geometric mean is that theorem that came up in section 6.1. When the altitude, okay, and we know from step 2, right, through step 2, we drew a perpendicular through a vertex to the hypotenuse. That is the definition of being an altitude. So when the altitude to the hypotenuse of a right triangle is drawn, each leg, what is each leg? Each leg is the geometric mean of what? Of the length of the hypotenuse. I think they just say of the hypotenuse. And the segment of the hypotenuse it is adjacent to. Okay, so that was corollary 2 from section 6.1. Okay, remember the theorem was that we have 3 similar triangles going on here in our geometry tattoo. Corollary 1 was that the altitude is the geometric mean of the 2 segments of the hypotenuse third one is the one we care about here because it allows us to talk us about B and A. We want it to be talking about these legs. We want to be talking about these legs. B squared plus A squared equals C squared. That's what we want to prove. So now we can talk about B squared. Check it out. Now we can talk about so why? Well, hey, up here in this proportion, what do we do if we cross multiply? B times B is B squared. D times C is what? Ooh, CD. Okay, so if I know that this is true, which I do from step 3, it all strings together. It's all connected, baby. It's all connected. If I do cross multiplication, and what your book calls that is the means extremes property from chapter 5. Okay, from chapter 5, or a property of proportions. You can just say that we're allowed to cross multiply, okay, to become this here. B times B is B squared, C times D is CD. We're good to go. What about this one? Cross multiply real quick. With me here. A times A is what? It's A squared. C times E is what? It's C times E, right? That's about as best as we can put it down. We have two variables multiply to one another. The best is we can just put them right next to one another, right? Put them right. You can't merge those together beyond that, right? This just simply means C times E, but there's no reason to put that dot there, right? Right next to one of them means C times Z. All right, check it out. Now we have this. That was the means extremes property. Cross multiplication. Now what we want to do is here, step 5, I've kind of given this to you. I said a B squared in this equation, A squared in this equation. I added them together, and I'm going to say it's going to be equal to something. That's what I'm asserting right now. A squared plus B. So hey, wait, if I add these left side of this equation together, and I add the right sides of the equations together. Remember, they're equations, they're statements of equality. What is my resulting equation? Well, it's equal also. So here, right, with my next statement, I'm making an argument to you. I mean, I wasn't expecting you to make this argument out completely on your own. That's why we talked through it together. If I do A squared plus B squared, well, that's got to be the same as CD plus CE, right? You say B squared is 100. A squared is 49. Well, that means CD is 100. CE is 49, right? This plus that, they both equal 149. So anyways, right? We have two equations. We can add the left sides together, add the right sides together, and equality is preserved. And what that is called is the addition property of equality. Yes, addition prop of equality. Boom, we got it. Yes. Cool. So now I got A squared plus B squared. That's fantastic. That's so good. Why? Because I have A squared, B squared on one side of an equal sign. And I want to get C squared on the other side. So now we got to do some work, right? And the only thing that we're away from proving this, freaking Pythagorean theorem, yes, like the most famous of all geometry theorems. The only thing that's standing us in our way is not the left side. Our left side is done. We're not going to simplify that or rewrite that. We're going to somehow have to rewrite this as C squared, or C times C. Now, your first step on this one is to realize that C is timesing D. C is also timesing E. And interestingly enough, look, if we multiply C times D, multiply C times E, it kind of is like multiplying C times C. But why? How can we prove it? Well, here, C times D times C times Z. There's a way we can write this out using the distributive property, right? If we write this one out using distributive property, sort of like reverse distributive property, otherwise known as like factoring algebra 1. C is a common factor of this term here. This means C times D plus C times Z. So what is C doing in both of these terms here? Well, the first time it's multiplying to D. The second time it's multiplying to E. And there we go. Via the distributive property, C times D is CD. And C times E is C times E, right? That's what we have up top here. Okay, so what your book says, I think in class they called it factoring. That's fine. You factored out a C, moved it to the outside, because C times D plus E is the same thing as CD plus E. Hopefully you can accept that. Your book says that is the distributive property of multiplication over addition. That's how they justify in the book, because they gave that, they mentioned that in section 1.4, and I'm like, you don't have to use the distributive property to do geometry, do you? Well, it wasn't for a really long time. So perhaps you forget about the distributive property, but that's exactly what it is. This times that plus this times that equals this, right? And vice versa. Anyways, distributive property here. All right, and that's all nice and good here. Step 7, I sort of skipped over something. Okay, I skipped over something. Right, this is what step 7 is predicated on, is that they have a D plus E here. C is going to be multiplied here. What is our goal? We want to multiply C times by C, okay, because that equals C squared. So question, I have C here. Is D plus E C? Why? Right, why? Okay, so let's pull it aside here. Sort of an unsaid step is this. D plus E, which I have up here, those are the two segments of the hypotenuse of the right triangle, D and D. So if I add them together, I get what? D plus E equals length C. This length plus that length got to equal the length of the whole segment because it composes the whole segment right there. So D plus E equals C, okay? And what that is the segment addition postulate. Part plus part equals whole when talking about partial segments, adding up to a whole segment. So that's the segment addition postulate. And that's going to be part of step 7. But really the key thing is here is we want to take this D plus C and we want to substitute C back into it. Because if we can do that, then we have C times C. And what does C times C equal? C times C equals C squared. And boom, we got it. A squared plus B squared plus C squared. What was the A? That was one length of one of the legs. What was the B? That was another length of one of the legs. Square both of them, add both of them together. The sum of the squares of each leg of the right triangle, length of each leg of a right triangle equals the square of the hypotenuse. We've gotten there. Last justification, segment addition postulate and substitution. So 7 steps. Is this hard? Is this hard to follow? Is it hard to come up with on your own? Yes, a little bit. But again, your goal, get in other people's heads. Learn how they think. Try to follow their reasoning. All important skills. Hopefully you're picking that up for me or you're picking up for your teammates or videos you're finding online. And we'll keep pushing forward. We'll keep experiencing it. We'll keep thriving, my friends. Email me if you have any questions. That is the Pythagorean theorem. Our proof. Is this the only way to prove it? No. So many proofs. So many proofs can be done. Have a good weekend. Bye.